Oh, okay. All right, so what we're going to be talking tonight is the loaded voltage divider. Loaded voltage dividers are used extensively in all different kinds of applications. The car that you have parked out in the parking lot, you probably have hundreds, if not thousands, of loaded voltage dividers in your car. In different parts of your ignition system and your GPS, and depending on how new your car is. The space shuttle probably has hundreds of thousands of loaded voltage dividers. And so what we're going to do is we're going to learn what a loaded voltage divider is, and then we're going to learn how to design a loaded voltage divider. And some of you may be saying, well, what do you mean design? What does that really mean? And I'll explain that to you, okay? So the first thing that we're going to do is we're going to take a look at an unloaded voltage divider. We're going to take a look at an unloaded voltage divider. Okay, so an unloaded voltage divider is really simply a circuit that looks like this. You've got some kind of a voltage source. Our book likes to call that E sub t. So let's just say that that's 12 volts, like you'd find in your car electrical system. Okay, and then you have connected in series with that battery 3 resistors. 1, 2, 3, and those resistors are all in a series configuration with each other. So I'll just label the resistors R sub 1, R sub 2, and R sub 3. Now if you look at some of the characteristics of this circuit, which again is an unloaded voltage divider, okay, what is it that we could say about the current that would flow in this circuit? In other words, would the current be the same everywhere, or would the current change as you went from resistor to resistor? The current's the same. The current's the same, right. And the reason is because, number one, the circuit is connected in a series configuration. And in other words, everything is coupled together. And if you look at it, the topology of the circuit, there's nowhere for the current to branch out. There's no place for it to take off in 2 directions, right? So if I follow around the circuit here, I find that there's only one path. There's only one path to go. The only other path would be to change directions. In DC, the only way you can change directions is to switch your polarity, okay? And really, when we start talking about AC, we start talking about switching polarity. Okay, so DC is a fixed polarity. So for a fixed polarity, if the positive is on the top and the negative is on the bottom, and we're talking about electron flow, the electrons are going to leave the negative terminal of the battery, and they're going to flow through this resistor, through this resistor, through this resistor, and then back into the positive terminal of the battery. And the current, every single place in the circuit, is going to be the same. It doesn't matter if you're talking about the wires, the resistors, the battery, it's all the same. And that's because they're in series with each other. Okay? Now, the experiment that we're going to be doing is going to be an experiment where we are going to take 2 different light bulbs. Now, I'm going to use a large version like you have at home, but what we're going to build is going to be on a proto board. So it's going to be those little tiny light bulbs like we used last time. Okay? Now, when you go to Home Depot and you buy these light bulbs, I'm looking at this light bulb, and this light bulb right here is a 60-watt light bulb. This light bulb is a 200-watt light bulb. Okay? That's the only thing it says. Well, it says, Westinghouse. Actually, this one's General Electric. So it says who makes it. One manufacturer actually puts the voltage that you're supposed to plug this into. Most don't. Like this one doesn't. They do not put any voltage at all. All they put is just 60 watts. And the reason that most of them don't put the voltage is because all the houses in the United States are wired up the same for the basic receptacles coming out of your wall, right? So you have 120 volts plus or minus about 7 or 8% coming out of your walls. So they know that if you have a light bulb that you're going to go, plug into a receptacle in your bathroom, or you're going to go out onto the porch and you're going to, plug a light bulb into a receptacle on the porch, the voltage that is going to be exposed, or that's going to drive the current through this light bulb, the electrical pressure, is going to be 120 volts. So they don't really have to worry about specifying it to you, because you would have to do something custom in order to change it. And if you would know what you were doing, and you would order things special, and so they try to make it as easy as they can for you. In other words, if you're getting a light bulb for grandma, and grandma wants a nice soft white light, to take a bath by, and just enough light in there so that she can see, kind of thing, and you come home with a 300 watt bulb, and she turns on the light, you're probably going to hear her screaming at you. I did not want a light bulb that bright. I wanted a dim light bulb, I wanted a 40 watt bulb or a 20 watt bulb or something like that, right? So that's kind of, I think, what we can all relate to in terms of ratings on light bulbs. Now, when you start getting into light bulbs that are used for other types of applications besides in your house, typically they're not all going to be at the same voltage. As a matter of fact, in general, they're not. And so rather than just having on the top of the light bulb what the wattage rating is, which kind of gives you an indirect sense of how bright it's going to be, there's actually a device which can measure the number of foot candles, or the brightness of the light bulb. Okay, but you know that a 20 watt bulb is going to be dimmer than a 200 watt bulb, right? And if you've had different bulbs and you've used them in different rooms, then you kind of get an intuitive sense of what bulb is going to work best in what room. And you don't need a meter that can measure luminance or foot candles, right? You just need to know what wattage you want in that room. What we're going to be dealing with is circuits where you can have light bulbs ranging from 1 volt, on up to 1,000 volts. You can have light bulbs that are drawing anywhere from microamps all the way into hundreds of amps. Okay? And so because of that, when you order the light bulb, and you can order light bulbs there's a Granger catalog, big industrial catalog that has all kinds of different industrial supplies. They have pages and pages and pages of different kinds of light bulbs. And when you look at the listing of the light bulbs, one of the columns is the part number, right? That's how you order it. And then another column will say what the voltage rating is on the light bulb. And then another column will say, how much current the light bulb is going to draw if it's operating at that voltage. And then another column might say how many foot candles it's going to put out. And then there might be other information too. But the main thing is the voltage and the current. Okay? So let's say that we had a circuit that we could build in this laboratory. And what we're going to do with this circuit in the laboratory is we are going to build a loaded voltage divider. Okay? We're not going to have an unloaded voltage divider. We're going to build a loaded voltage divider. And all that means is that we are going to take, and I'm going to draw this in a different color, I've already done this once. I don't think that that the tape's on the website yet, but it will be by the time you get home tonight. But you'll notice that I did this with one load, and what you're seeing now is a more practical applications where you have multiple loads. Okay, and so what I'm doing is I'm drawing with blue pen here to show what constitutes the difference between a loaded and an unloaded voltage divider. Okay, so the part of this drawing or schematic right here that's in blue is the part that makes it loaded. Okay, so in other words, you have made a connection here. Would this be considered a series or a parallel connection between R3 and let's call this light bulb number 1? That'd be a parallel connection, right? That would be a parallel connection, okay? What would the connection be between R1 and R2? That would be a series connection, right? Exactly. What would the connection be between R2 and R3? Careful, careful now. It's actually what we call a combination connection. It's a combination connection. And the reason is because we've already said that it would be fair and accurate to say that resistor 3 is in parallel with the light bulb, right? Okay? Now, there's a formula that we can use that's in our book and that I've lectured on, okay, where we can combine those two loads, if we know the resistances, we can combine those two loads into one load. So in other words, I could erase both of these loads and I could draw one resistor. And that one resistor would represent the effect of these two, well, this resistor and this light bulb being in parallel with each other. Now, if I did that, if I erased this and I drew one load, then R2 would be in series with it, wouldn't it? Okay? But if I haven't done that, if I haven't simplified this part of the circuit, then I can't say that R2 is in series with R3. Nor can I say it's in parallel. What I can say is that R2 is in series with the parallel combination of R3 and the light bulb. Let me say that again. R2 is in series with the parallel combination of R3 and the light bulb. That's what you can say that's accurate. Okay. What we're going to be doing with this loaded voltage divider is we're going to be taking one light bulb and we're going to be connecting it in parallel with R3, and then we're going to be taking another light bulb, which I'll also draw in blue, and we're going to be connecting it in between R1 and R2. Okay? Now, this is the challenge. This is the assignment. This is the lab. The lab is to take our regulated DC power supply, right, which we learned all about last time, right, our regulated DC power supply, can't burn it up, can't shock ourselves with it, safe to use in a fundamental electrical lab, okay? And this thing is actually a variable DC supply. Whenever you see something with an arrow going through it at 45 degrees, that means that it has the ability to be turned up and down. Okay, it's variable. So if you see a resistor with a line going through it, that means it's a variable resistor, also called either a potentiometer or a rheostat. Okay? Now, for the regulated DC power supply that we have in this lab that we used last week, okay, how high can the voltage go up before it can't go up any higher? 18 volts. So this can go from 0 to 18 volts, and this is DC, right? Because there's a DC component to the course and an AC component to the course. What does DC refer to? Direct current. What does AC refer to? Alternating current. Direct current means the current is always flowing in one direction. Alternating current means that the current is always changing directions. As a matter of fact, in this room, the lighting, or the current that's flowing to the lighting, is changing direction how many times a second? 60 times a second. 60 times a second, right? So I want somebody to snap their fingers 60 times in 1 second. I mean, it's fast, right? Right? Because if I stomp my foot 1, 1,000, 2, 1,000, that's 1 second. Snap your fingers 60 times. You can't do it, right? It's fast. And 60 hertz is not fast. If you went to Best Buy and they said, hey, we've got this new laptop and this thing's running at 60 hertz, you know, you'd probably be smart enough to turn around and walk out, because, you know, microprocessors are running a lot faster than 60 hertz. We transmit power at 60 hertz. We don't run computers at 60 hertz. Okay. Now, there's a couple of things that we have to know before we start. One of them is that we have ordered these light bulbs, and the ones that we're actually going to use are miniature versions of this. But we have ordered these light bulbs from a catalog. And the catalog has given us the ratings of the light bulbs. So this is not something we can change. We're stuck with it. If you go buy a brand new 500 horsepower Cadillac, you know, you're stuck with that 500 horsepower Cadillac. And if you tell them, I'd rather have a 100 horsepower Cadillac, they're going to say, well, we don't make them. You know, you want to put a governor on it or something, you're going to have to go have it modified, right? So when you buy the light bulb from Grainger or from some company that sells light bulbs, they're going to have, you know, certain light bulbs, and that's all they've got. Now, they may have 100,000 of them, but that's all they've got. Okay, so what we've done in the lab is we have selected 2 different light bulbs to be our loads. Okay? Now, what's important to us are the ratings. The ratings of the light bulbs. Okay? We have 2 light bulbs. We're going to call this guy down here light bulb number 1. We'll call this guy up here light bulb number 2. Okay? And I'm going to tell you what the ratings are. And again, this is not something that I made up. This is something that I ordered out of the catalog. Okay? Light bulb number 2 has the following ratings. It's rated to operate at 14 volts DC, okay? And it's going to draw 80 milliamps when it's operating at its full brightness, okay? Light bulb number 2 is a light bulb that is rated to operate at 6 volts DC. And when it's operating at 6 volts and putting out its rated and drawing its rated current, it will draw 200 milliamps. Did I see a question?
Yeah, you mean light bulb number 1.
I'm sorry?
Light bulb 1 or 2 is which?
Light bulb number 2, oh, I'm sorry, you're right, I switched them. Thank you very much. This light bulb right here is down here. So this is light bulb number 2. This light bulb right here is up here. That's light bulb number 1. Is that better?
Look at where you have the 14 volts.
Uh-huh.
They're both labeled light bulb number 2.
Oh, thank you. Thank you. This is light bulb number 1. So this is the light bulb that's going to have the higher voltage. This is the light bulb with the higher voltage. Okay? This is the light bulb with the lower voltage. This is the light bulb with the lower voltage. Thank you. That was just an oversight. Okay. So we now have the ratings of the light bulbs. And what we're stuck with is the following dilemma. Okay? How are we going to get both of these light bulbs to operate at their rated brightness when we only have one battery? Think about that for a second. We've got a light bulb that wants 6 volts down here, right? This is the 6-volt bulb. This light bulb wants 6 volts. This light bulb wants 14 volts. Okay? And we've got only one source that we can turn up as high as 18 volts and no higher. First of all, is it going to be possible for us to operate these light bulbs at 2 different voltages at the same time with only one source of power? Do you think? Well, the answer is yes. The answer is yes. And so the question is, how are we going to do it? Well, this is how we're going to do it. We are going to use the following principles that we should already be familiar with, but that we will review as we go. Okay? The first one, I'll get a pin that's working here. The first one, the first principle that we're going to use to solve this circuit right here is going to be Ohm's Law. Everybody's familiar with Ohm's Law, right? You got the wheel with the formulas. You can calculate power, voltage, resistance, current, based on different formulas, okay? So we're going to need the Ohm's Law formulas in order to design this circuit. We are also going to need to know Kirchhoffs voltage law. Okay? What is Kirchhoffs voltage law? Does anybody know what it is?
Sum of voltage around any closed loop must equal 0.
Exactly. The sum of the voltages around any closed loop must equal 0. And this is something that I've gone into in quite more detail on previous lectures, which you probably haven't watched yet. But that's the main definition of Kirchhoffs voltage law. And it fits the scientific model. In other words, it always, always, always works. If you have a closed loop, the sum of the voltages around that closed loop will be equal to 0. Okay? Now, that is kind of an abstract statement. The practical way of stating Kirchhoffs voltage law is, and let me move over to this board here to the right just a little bit to give you an example. Let's say that we just had a circuit here where we had 20 volts for our supply. Our battery was 20 volts, okay? And we had 2 resistors. Well, let's say 3, since our unloaded voltage divider has 3 resistors. Resistor 1, resistor 2, resistor 3. This is what Kirchhoffs voltage law says. Kirchhoffs voltage law says that the voltage here must be equal to this voltage plus this voltage plus this voltage. Okay, so where does the 0 come from? The 0 comes from the polarities. In other words, if you look at the polarities on these resistors and compare it to the polarity here, then when you go around the circle, it does equal 0. Okay, but in practicality, the way we use Kirchhoffs voltage law is that we say that this source voltage must be equal to this voltage drop plus this voltage drop plus this voltage drop. So if I told you that I had 10 volts that was dropping across this resistor, and I had 15 volts, I had 5 volts that was dropping across that resistor, then by Kirchhoffs voltage law, how much voltage would there have to be dropped across resistor 3? 5, right. Because 10 and 5 is 15, and we have to get to 20. So we have to have 5 volts here. Okay? So that's Kirchhoffs voltage law in a nutshell. So let me erase this and move back to our design parameters. We're going to have to know and use Kirchhoffs voltage law to design this loaded voltage divider. Okay, and again, what are we trying to do? We're trying to use one voltage source that we're going to turn up all the way. Okay, so what I'm going to do is I'm going to erase the 0, and I'm just going to leave the 18, because I don't want you to get the impression that, you know, we can turn it up and down, which we can, but we're going to turn it up all the way, and that's the way that we want it to operate, you know, indefinitely without burning up. Okay, so we're going to have one DC power supply, and it's going to be connected to these 3 resistors, and then these light bulbs are going to be hooked in at these points that we call nodes. Okay, so the current obviously can branch off in different directions. Okay, so we're going to need to know Ohm's law to design this circuit. We're going to need to know Kirchhoffs voltage law. We're also going to need to know Kirchhoffs current law in order to design this circuit. Okay? And then the fourth thing that we're going to need to know to design this circuit is what we call an industry standard. An industry standard. In other words, there is an industry standard in the state of California that handicapped parking spaces are a certain number of feet wide. Right? Now, it may vary between counties. I'm not sure about that. But I think that for the most part, they're all, you know, within a few feet of each other. They're obviously wider, and they have more space for, you know, disabled individuals to get out, like with a wheelchair, with a walker, or something like that. Okay? But that's a standard. So if you're going to build a parking lot, and you build all of your handicap parking so that the space is only half as wide as, you know, some law requires or some statute requires in the city ordinance, then they're not going to let you open up that parking lot to the public, because they're going to say, look, you know, you're discriminating against handicap because they can't get out of the cars. Okay? The industry standard that we are going to be using here is an industry standard that has been developed by people that make these devices, called voltage dividers. Okay? Now, voltage dividers are used very widely in the power industry. Let me give you a very quick example. Think of driving down Highway 1 and driving underneath the overhead lines, okay, that go between Cuesta College and Morro Bay. Everybody know what I'm talking about? Just before you get to South Bay Boulevard, you've got those high tension lines, right? And they've got those like donut looking things that are around the lines. Does anybody know what those donut looking things are for?
I'm not sure. One thing that I have
exactly right. That's exactly right. It's for low-flying aircraft, primarily helicopters, but also for planes, because take somebody who's a pilot who's not instrument rated, and they take off and the weather's nice, and all of a sudden the weather turns bad and they've gone a little further than they had originally planned, and they're trying to find their way back. They're going to try to find a landmark. And if they can see a highway and they can get down low enough so they can follow the highway, then they can just follow the highway back all the way to Burbank Airport or wherever they're headed, right? And so the idea is that the power company doesn't want some Cessna flying along or some helicopter flying along and running into their 500,000 volt high tension line, because it's extremely expensive and it's going to cause major power outages in lots of places. Okay, now if we had, let's say that this is one of those lines that's up in the air, and let's say that we're having some kind of problem. So I've got a line that I've drawn here, and this represents a high voltage line, transmission line, okay? This represents a high voltage transmission line. And there's some kind of a problem with that high voltage transmission line. If you look closely at high voltage transmission lines, the cables don't run forever, okay? There are certain places where they have to use couplings, and they have to actually crimp the lines together, just like you do with, wiring a car. Just like crimping a spade connector to, hook up a radio in a car. The power company has to do the same thing. Every so often, they'll get to a point where they run out of line, okay, and they have to put a coupling. And it's usually not very much bigger than the line. But let's say that over time that coupling has gotten loose because of vibration in the line. Because anytime you have an electrical line, there's vibration of the crystalline lattice of the line. Okay, it's just a phenomenon of nature. Anything above 0 degrees Kelvin is vibrating. Okay, and so let's say that they identify through thermal or infrared inspection with cameras that there's a hot spot right there at that coupling. Okay, and so they want to go up and they want to take more measurements before they decide exactly what they're going to do. Okay, well, one of the things that's done very widely with linemen and electrical workers is they'll have the line de-energized very briefly. Some utilities work hot with the lines, hot, but most utilities will de-energize a 500,000 volt line before they send a worker up there to make a connection to it. Okay. So the worker goes up there, makes a connection to the line, and then the worker has a truck that's parked down here, and it's a panel truck sitting on wheels. And inside the panel truck, there's different kinds of instrumentation. There are oscilloscopes and meters and power supplies and spectrum analyzers and dynamic signal analyzers and all kinds of stuff, okay? All kinds of fancy equipment. And what they want to do is they want to be able to get a sample of the voltage signal that's riding on this line down here in the truck. Well, obviously, you can't bring the line straight into the truck. You can't do that. Because if you did that, you'd be bringing 500,000 volts into a truck. And they don't make safety equipment that's rated that high. Somebody's going to get killed. So what they do is they sell these large voltage dividers that you can buy. And basically, what they look like are big donut rings. They're called corona rings. And inside the corona rings are resistors. So there'd be like 2 resistors, and then there would be a copper rod that would be pounded into the ground. So let's take the copper rod all the way down to the ground down here. So our copper rod is going to go down to the ground, and then it's going to be pounded into the ground like that. So that's our ground. And then what we're going to do is we are going to have a resistor here on the top and a second resistor here on the bottom. And then in the center, we're going to have a coax cable that allows us to bring a wire out and bring it right into the back of our work van. Well, it turns out that they make high voltage dividers that are rated for 500,000 volts coming in and 120 volts going out. Okay? Now, they used to use these things hooked up directly like this. Problem with this is that if the voltage divider fails, in other words, there's a short circuit and the thing flashes over, okay, then for a very short period of time, you're going to have that full 500,000 volts inside the van. And we've had, with the power utility I worked with, we've had several people killed with a scenario just like this. So what we do now, what all utilities do now, is they use fiber optics. So they'll feed the signal coming out of the voltage divider into a fiber optic transmitter receiver pair. So they'll feed it into a transmitter, and then they'll run like 500 feet of fiber optic cable. Who knows what fiber optic cable is? What's it made out of? Glass. Glass and a coating around the glass, which can be many different substances ranging from like what you'd find in an extension cord or rubber type substance to Kevlar, okay, for tactical military operations. But the bottom line is that if you have 500 feet of fiber optic cable, okay, and your voltage divider fails 500 feet that way, okay, then the only thing it's going to do, it's going to blow up your little transmitter, your fiber optic transmitter. There's going to be no galvanic conduction. There's complete galvanic isolation, meaning that you're completely insulated electrically. You're completely protected electrically through that 500 feet of fiber optic cable. Okay, and so that's how they've, gotten away from worrying about, their employees getting killed by doing these measurements is with fiber optics. But they still use the voltage dividers to get the voltage from something that's so high that you can't work with it to a value that you could plug right into one of the instruments that's on one of the benches that you're sitting at here in this lab. Okay? So this is very, very practical. Okay, it's used in all the industries. Now, the industry standard that we're dealing with, okay, with the design of our loaded voltage divider is one of efficiency. Okay? And so what we're going to do is we are going to follow basically what the designers and builders and distributors have learned over the past 50 years that have been building these things. Because they've built them, probably hundreds of different ways. And they've found out what is pretty much the most economical way to build it for 90% of the applications. Of course, you're always going to have some special application where it's going to be different. But the one industry standard that applies to about 90% of industry loaded voltage dividers is that the current that's flowing through the bottom resistor resistor number 3, that would be this current right here, where I've drawn the arrow, okay? That is going to be equal to 10% of whatever the current is that's flowing through light bulb number 2. Now, that is arbitrary. That is not based on, Kirchhoffs voltage law, Kirchhoffs current law, Ohm's law, the Kramer's rule, the law of gravitational fields. It's not based on any real scientific principle. It's based really mainly on economics. Because if we had the current that was flowing through this resistor be equal to 90% of the current that's flowing through the light bulb, then guess what happens to the cost of this resistor? Would it go up or down? Would it have to be a beefier resistor, or could it be a small, tiny little quarter-watt resistor? It would have to be a big, beefy resistor. And so as a result, it would cost a lot of money. Okay? And so this industry standard right here is driven by profit of the people that make them. And so we're simply following what you read about if you study about loaded voltage dividers. We're following that industry standard. Okay, so when we design this circuit, and I use the word design fairly loosely, but really it's what you're doing when you design pretty much any circuit. You're figuring out the ratings of the components in the circuit so that it works. In this circuit, we already know what the rating of light bulb 1 and light bulb 2 are because we purchased them out of a catalog and we had no control over them. Okay? What we do have control over is the value of this resistor and its wattage rating. The value of this resistor and its wattage rating. The value of this resistor and its wattage rating. Okay? So figuring out the values of these resistors in terms of ohms or opposition to current flow, as well as power dissipation, is designing the circuit. That's what we mean by designing the circuit. Okay, so I'm going to move through this, relatively quickly. So if you have any questions, stop me because we're taping it, and you can watch it, you can rewind it. Okay, if we look at light bulb number 2, which is our bottom light bulb, okay, how much current is flowing through that light bulb? How much current is flowing through that light bulb? 200 milliamps. Would it be reasonable to say that 200 milliamps is the same as 0.2 amps? Right? If you've studied your metric conversions, dimensional analysis, okay, converting from milli to base unit, 200 milliamps, we would move the decimal over 1, 2, 3 places. So the decimal would be right there. Okay? So that would be 0.2 amps. Okay? So we have 0.2 amps flowing through that light bulb in order for it to be operating properly. Okay? How much current would be flowing through this resistor right here if we were going to stick to the industry standard that we read about if we research these devices on the internet? I'm sorry? 20 milliamps. So that would be 20 milliamps. And if we wanted to convert that to base unit, then we would move the decimal over 1, 2, 3 places. So that would be 0.02 amps. Are you with me? Is that right? Okay. So based on this industry rating right here, the current and I'll go ahead and draw it out here, the current that would be flowing through this resistor would be 0.02 amps. Okay? Now, the next question. Any questions so far? The next thing that we're going to do so that we can progress in designing our circuit is we're going to use Kirchhoffs current law. What does Kirchhoffs current law basically say?
Sum of the current entering and leaving point must equal 0.
Right. The sum of the currents entering and leaving a point or a node must be equal to 0. Okay, that's kind of an abstract way of saying whatever goes in has got to come out. If you have a closed system, whatever comes into it has got to come out. So if you have a water tee, okay, and you have equally sized piping in your backyard in your sprinkler system, and you got 10 gallons per minute of water that's flowing, and it flows into a water tee, and the water tee has pipes that are equal size, how much water is going to be coming out of each part of the tee as it splits? 10 gallons per minute comes in. How much comes out here and here? 5 and 5. Right. So 5 plus 5 has to equal 10. Okay? So if we were to look at this point in the circuit right here, how much current is coming from the light bulb into this point or node? 0.2 amps. And how much current is coming into this point or node through this resistor based on the industry standard? 0.02. So what would be the current that would be flowing through resistor 2? Let's write it down here. The current flowing through resistor 2, and this is by Kirchhoffs current law, the current that's flowing into resistor 2 has got to be equal to the current coming from resistor 3 plus the current coming from light bulb number 2. That is a statement of Kirchhoffs current law. It's also a statement of the law of conservation of energy. In other words, whatever comes in has to go out. You got current coming out from this node or this point. It's got to be coming from somewhere. Well, it's coming from two places. One is from the light, and the other place is from this resistor. So this current plus this current must be equal to this current. Okay? So that current is equal to, the current in resistor 3 is 0.02 amps plus the current in light bulb number 2 is equal to 0.2 amps. And so that's equal to 0.22 amps. Are you with me? Okay? So would it be fair to say that the current that's flowing through this resistor right here, I'm going to redraw it over here, would it be fair to say that that current is equal to 0.22 amps? That would be fair to say, right? Okay. Now, how about the current that's flowing through this light bulb number 1, assuming that it's operating at its rated condition? How much current would we expect to be flowing through that light bulb? 80 milliamps. But if we want to express it in base unit, let me erase my utility truck here. Okay? Then we're going to have to move the decimal over 3 places, right? 1, 2, 3. So that would be equal to 0.08 amps. Right? So we've converted from milliamps to the base unit of amps. Okay? So the current flowing through this light bulb is 0.08 amps. So this is 0.08 amps. Okay? Now, would it be true that the current that's flowing through resistor number 1, in other words, this current right here, we'll call it IR1, would be equal to the current coming through resistor 2 plus the current coming from lamp number 1? Would that be fair to say? Okay, so let's write that down. Down here, by Kirchhoffs current law, the current that's flowing through resistor 1 would be equal to the current that's flowing through resistor 2 plus the current that's flowing through light bulb number 1. Would that be a fair statement of Kirchhoffs current law? In other words, whatever goes in has to come out. Law of conservation of energy. Okay? So the current that's flowing through resistor number 2 is 0.22, right? So that's equal to 0.22 amps plus the current from light bulb number 1 is 0.08, right? 0.08 amps. So what is that equal to? 0.22 plus 0.08. 0.3 amps. Is that right? Okay. So this is equal to 0.3 amps. So now we've just figured out what all the currents have to be in our voltage divider circuit in order for it to be functioning properly. Okay? We haven't yet, though, figured out what all of our voltages have to be. Why would we have to figure out our voltages? To figure out the resistors. With Ohm's law, if we're going to use Ohm's law to pull out an equation for resistance, what is going to be the most likely equation that we're going to use if we're going to have information about voltage and current? Just look at your Ohm's law wheel. What's resistance equal to in terms of voltage and current? E over I. Resistance is equal to E over I. So if we know the voltage everywhere and we know the current everywhere, then can we figure out what the resistance values have to be? Yeah. That's called designing the circuit. Okay. So let's come down here first and let's take a look at the bottom of the circuit and work up. Okay? What do we want the voltage to be across this light bulb in order for it to be putting out its rated foot candles? 6 volts. Okay? Would it be a fair statement to say that this is a closed loop? Yes. That's a closed loop. Okay? What is Kirchhoffs voltage law? Or what does it say?
The sum of the voltage drop across all the resistors must equal 0.
The sum of the voltage drops around any closed loop must be equal to 0. Which basically means that if you have a closed loop and there's only 2 things in it, and you know that the voltage on one of them is going to be 6 volts, what's the voltage on the other one? 6 volts. Right. So this is going to be 6 volts. Okay? Now, what about light bulb number 1? What's the voltage drop going to be across light bulb number 1 if it's going to be operating at the rated foot candle output. Yes, question.
Of that first closed loop, why is that resistor number 3 6 volts instead of 12? Because don't you have 18 volts that you have to equal total?
You have to equal 18, well, you have to equal 18 volts total in this closed loop. Right? Do you notice how you have several closed loops? In other words, this right here is a closed loop. I don't mean that current can't get out of it. I just mean that in terms of voltage, okay, it's a closed loop. Okay? This right here is also a closed loop. Okay? And then finally, this is a closed loop. So, your question about how we're going to address the 18 volt source, we're going to introduce that part of the circuit when we're figuring out the voltage drop here. Because Kirchhoffs voltage law says that 18 must be equal to this voltage drop plus this voltage drop plus this voltage drop. Why? Because this is a closed loop. You got me? Okay. And obviously, this closed loop right here is not the same as this closed loop, because this closed loop doesn't even have a battery in it. Right? So they're different. Okay. So we know that this light bulb has a voltage drop, or we want it to have a voltage drop of 14 volts. Okay? So if we want that to have a voltage drop of 14 volts, then would it make sense to use this closed loop right here? Okay? Because we know that this is 14 volts. And I'll just put a square around it because I'm getting kind of tight for room. This is 14 volts. We know that this voltage must be equal to this plus this. Okay? So 6 plus what equals 14? 8. So would it be reasonable to say that there would be an 8 volt drop across R2? Yes. That would be applying Kirchhoffs voltage law to this closed loop right here. Okay? Now, let's go to the question that you addressed, and that was, what about the 18 volt source? Okay? So now I'm going to go to the biggest closed loop. The biggest closed loop, using Kirchhoffs voltage law, 18 volts must be equal to this voltage drop plus this voltage drop plus this voltage drop. So 6 plus 8 plus what equals 18? 4. So this is going to have a 4 volt drop across it. Okay? So what I'm going to do is I'm going to erase the industry standard just to give us a little bit of room over here. And now what we're going to do is we're simply going to apply Ohm's law. So by Ohm's law, we know that resistance is equal to the ratio of voltage divided by current. So resistor 1 would be equal to the voltage drop across resistor 1 divided by the current flowing through resistor 1, which would be equal to 4 volts divided by 0.3 amps. 4 volts divided by 0.3 amps. Are you with me? Okay, what is that? 13.3. Okay, and so what we're going to do is just kind of round up, because we're not going to find a 13.3 ohm resistor. So we're going to let this be 14 ohms. So that's going to be 14 ohms, so we'll put a box around it. what about resistor number 2? We know that's going to be equal to the voltage drop across it, right, which is 8 volts, divided by the current flowing through it, which is 0.22 amps. What do you get when you take 8 divided by 0.22? 36.4? Okay, so we're going to just go ahead with around a 36 ohm resistor for R2. Okay? And then for R3, that's going to be equal to voltage divided by current. So it's the voltage drop across resistor 3, which is 6 volts, divided by the current flowing through resistor 3, which is 0.02 amps. So what do we get for that? How much? 300. 300 ohms? Is that right? Okay. 300 ohms. So in boxes, 14 ohms goes there, 36 ohms goes there, 300 ohms goes there, and all of a sudden our circuit works like a charm. You've got 2 light bulbs operating at different voltages, and they're glowing at their rated foot candles. It's kind of cool. Now, your job between now and next Wednesday is to figure out what the power ratings need to be on these resistors. And you have plenty of information to do that, right? You're going to go to Ohm's Law, and if you want to, you can use power equals I squared times R. Or you can use one of the other 2 equations. Now you're going to figure out what the wattage rating of each one of these resistors needs to be, and then you're going to build the circuit. And when you're done building the circuit, it's going to look something like this. Here is the bottom resistor, resistor 3. Here's resistor 2. Here's resistor 1. The source is going to be hooked up out here where my fingers are. So our regulated source is going to be here. Here's our 14 volt incandescent lamp. Here's our 6 volt incandescent lamp. Any questions? Okay. Do your power calculations, and if you have anything you want to talk to me about individually, come on up and I'll be happy to talk to you.